All right, here's a video for 13.2. We're going to go back to Hooke's law. We did a lab with this, if you remember, where you had one spring and then two springs parallel and two springs end to end called series. And we got graphs like this. The spring force was proportional to the change in length of the spring. That gave us the equation, the Hooke's law, Fs equals k delta x, where k is the slope of that graph. And suppose I take some object and I pull it to the right. The spring force will be to the left, and I'm going to pull it out some distance a from its equilibrium position where x is 0. The displacement's to the right, I pull to the right. If I were to find the work done by my hand, it'd be the force applied d cosine theta. The force applied would be k delta x, but the force keeps changing from 0 all the way up to k delta x. And we said that that average spot right there would be 1/2 k delta x. So that's my average force. If I plug that in, multiply by the displacement, we moved it from 0 to a, or we moved it a distance delta x, times the cosine of the angle between these two is 0, gave us our 1/2 k delta x squared, which was our change in spring potential energy or elastic potential energy. This is equal to negative the work done by the spring, because as we pull to the right, spring force pulls to the left, and so the angle would be 180. So the work done by the spring force would be minus 1/2 k delta x squared. But we can think of it instead as a change in spring potential energy if we include the spring in our system. All right, now, what if we did the energy of the spring? Here's our conservation of energy equation, and at the beginning, the object has no speed. We just hold on to it. We let go. It does have a spring potential energy, 1/2 k delta x squared, and our delta x is going to be a. We're going to figure out how fast it's going at any point where it just has a final. This works for any spot along its oscillation back and forth. It might have kinetic energy and it might have some spring potential energy as long as it's not there. When it's there, it won't have any spring potential energy. And when it's way over here and stops, it won't have any speed. And so I'm going to plug in the distance we started at. The delta x was a. Okay, so here's a general equation. And then the book does a problem. It does several different types of problems, or similar problems. Let's solve one of them where it stops, like say right here. How fast is it going when it's halfway but to a? So a over 2. It would also work for the other side, by the way. It wouldn't matter. A over 2 to the right or a over 2 to the left from the equilibrium position. So this is just a constant. 1/2 k a squared is our initial energy, the spring energy of the block spring system, if you will. There's no kinetic energy, no gravitational potential energy, and no work is being done because this is a frictionless surface. So we would get, we're going to try and find, cheated. Okay, this shows us a couple things. One thing it shows us is, when is this going the fastest? It's going the fastest when this term is the biggest, and this is a constant. So this term is going to be the smallest if we want to make v the biggest. Well, what's the smallest we can make delta x? We can make delta x 0 right there when it gets back to its equilibrium position. So if we get rid of this term altogether, right, we'd be able to solve for the speed right there will be the maximum. So maximum speed is when delta x is equal to 0. And so 1/2 k a squared equals 1/2 mv squared, and this term is 0. If we multiply both sides by 2, we get k a squared equals m v max squared, and solving for v max, you get the square root of k a squared over m, or if you want to pull out the a, you get a over root, or times root km. Now, I would not memorize this. I would just be able to go back to here. You do probably want to realize, though, that it's going the fastest right here when it's when the spring is back to its relaxed length. That's when there's no force on the mass. The spring is back to its relaxed length. That's when it's going the fastest. We could also look back up here and say, when is the potential energy the greatest? Well, the potential energy is the greatest when it's not moving, when the speed is 0, which will be here when we let go, and also way back over here when it comes to rest, and over here when it comes to rest again. We showed in 13.1 that the spot that it moves to when it gets to the left-hand side will be the same as the spot that it gets to on the right-hand side. That is, that over here, this A will be the same as that A. That distance is the same. Again, I wouldn't memorize this. I would just be able to rederive the maximum speed is when this is 0, and all of the spring potential energy here has turned into all kinetic energy there. All right, and I spoke too quickly before, too early about solving for the speed when it's, say, A over 2. So we could do that. If we wanted to do that, we would still start here, 1/2 Ka squared. It's going to have a speed, we think. We're stopping, we're going to, right, when that's, we're going to stop our mass here when it's there, or on the way back, or on the way over here. Some spot, any spot, A over 2 away from the equilibrium. Doesn't matter if we're going to the left, doesn't matter if we're going to the right. How fast is the mass going? Equals 1/2 K A over 2 squared. So we can get rid of all of the halves. We get Ka squared equals mv final squared plus Ka squared over 4. So if you subtract this from both sides, that's a whole minus a quarter is 3/4. A squared is mv final squared. And we can divide both sides by m and square root. So 3a squared over 4m square rooted. And you can get that, oh man, it ran off, sorry, just off the page there, off the screen. So we can get that speed if we wanted. Again, you're not memorizing this. This is just at x equals a over 2. That would be the speed. That's kind of like just a practice problem, if you will. Okay, that's energy for a horizontal spring where it's oscillating back and forth across a frictionless table. What if we had something where instead we hang the spring vertically? Okay, so we have a vertical hanging spring, and we are going to attach a mass to it, and we're going to hang the mass, if you remember, it's gently and slowly until it hangs from the spring. It's not boinging at all. We're going to gently lower it. If we do the free body diagram, spring force up, gravity down, picked up as positive, Fs minus mg equals ma. So k delta x equals mg. We had all of this before in a previous chapter. Nothing so far in 13.2 is it really anything particularly new up until this point. We haven't really talked about what happens if we let this thing vibrate. So what if we were to pull this down a distance a and let go? If we pull down a distance a, the spring force is going to get bigger while gravity stays the same. So the net force is going to be up, and it's going to start, when we let go, it's going to accelerate upward. And actually, the acceleration will be upward all the way up until it gets back to its equilibrium position, is what they call it, when the force up equals the spring force up equals the gravity down. But it will already have a speed there, so it's going to shoot past this point. I'm going to figure out kind of, start thinking about how high up this goes, but we're going to kind of get to it in a roundabout fashion. And what we're going to do here is we are going to pick, there's different ways to do it. We're going to pull it down a distance a, okay, from that spot, which was the equilibrium position. Okay, so it was hanging there already, and I take this mass and I pull it downward and let go. Okay, so let's write some energy for this. You can pick the h equals 0 spot to be wherever you want. I'm going to pick it here at the equilibrium position. Okay, so we're going to have E naught plus work external equals E final. And the E naught, what kind of energy do we have at the beginning? Well, the spring has stretched, but it has stretched more than A, because if you really remember, we want the distance all the way from there, and we've come all the way down here. So we've gone down here and then down to A. So I'm going to draw this over here. This distance here, I'm going to call E just for the equilibrium spot, how far we had to come down so that the force up was equal to the gravity down. And then I'm just going to redraw A here just so it's easier to look at. And then we're going to have the initial spring potential energy is 1/2 K, and that stretch is A plus E, and we have to square it, 1/2 K delta X squared. Is there gravitational potential energy? Yeah, it's actually downward, mv G, it's below the 0 spot, so minus A, it's got negative gravitational potential energy. If we pick this spot as 0, equals, I'm sorry, it's not moving, I'm holding it. When I let go, it's still basically at rest. No work external being done, so just plus 0 here. I'm not going to write it. And then what we're actually going to do is we're going to figure out how fast it's going when it goes through this equilibrium spot. So it's going to have a speed 1/2 mv squared. It is going to have a spring potential energy, and now when it gets back to here again, it is stretched down just E. Right? We're finding out how fast it's going when it gets back to here. It has a speed. The spring is still stretched 1/2 k. Delta x is just E. And then the gravitational potential energy is mg h final, but h final is 0 because that's where I picked the 0 spot to be. We're figuring out how fast it's going when it gets back to there. All right, now there's some math here involved. And the math really isn't the main point. It's the result. That's the interesting result that's going to help us. 1/2 k, we have to FOIL first. We're going to get 2 of these terms, remember? A squared plus 2ab. So we're going to get 1/2 times 2. And I'm going to write actually KEA. I'm just going to switch them. Plus 1/2 KE squared. And this looks nasty right now, but it'll look good soon. I'm just going to keep going here. And the first thing to notice is these 2 terms are the same. So I can subtract them from both sides. They go away. But there's something else interesting to notice. This KE. Well, KE, right? Back up here when I had K delta X equals mg when it's just hanging, E is actually that delta X where it hangs. So KE equals mg. When it's hanging, delta X is that distance E. So this term right here is nothing more. KE is mg. So 1/2 K A squared plus mg A minus mg A equals 1/2 mv squared. But these 2 terms are the same. So they add to 0. And we get 1/2 K A squared equals 1/2 mv squared. And it's interesting, the gravitational potential energy term always cancels out when we're finding the speed through the middle. And if you think back to 13.1, actually, sorry, early on the previous page in 13.2, we had this. How fast is it going? At its fastest, in the middle, it's 1/2 Ka squared equals 1/2 mv squared. We use that to find the maximum speed, but the point is, when it's at this 0 spot on a horizontal spring, the equation 1/2 Ka squared equals 1/2 mv squared is the same equation we get when it is a hanging spring. The gravitational potential energy always cancels out. So, what that means is, we can think of a spring hanging vertically. And this is a bit hand-wavy. There's a much longer proof, but the idea here is that this now is like a horizontal spring if we were to turn this, say, sideways, right? But it's vibrating back and forth. It's going to go A this way and not E this way, but A that way, and go back and forth as if it were a horizontal spring. Not oscillating about the spot where the spring is relaxed, but oscillating about the equilibrium position where the mass is hanging from the spring and the forces left and right, or sorry, up and down really, are equal. So we can use that for later when we talk about periodic motion. We will have the same setup for a horizontal spring shaking back and forth. It will be the same type of equation if we pick this as our 0 spot where the spring is at its relaxed length. It'll be the same equation as if we use a vertically hanging spring, but instead of the 0 spot being here, we could do that and do a lot more math, or we can just imagine it oscillating about this the equilibrium spot where the force up equals the gravity down, and it will vibrate up and down. So just to draw it, I won't draw it. If it were to go way down here, it would go way up there. So it's not going to go back up just E. Thanks, guys.